The edition you can take third edition or above. The reference books you can follow are digital image processing using MATLAB, and also there is Fundamentals of Digital Image Processing by Anil K. Jain, A.K. Jain. So this is also a very good book. But for the course, we will follow the Gonzalez and Woods book. Okay, so the course will flow like this. First, we will see in initial lectures the introduction to digital image processing. Then we will see the enhancement techniques in the next lectures. The enhancement will consist of a spatial domain processing and frequency domain processing techniques. Then we will see the restoration and reconstruction of images. So that will be actually the improvement of the images when they are received from a communication channel. So we will try to model the corruption by noise of the images. Then there is image compression. So image compression is you can say it is a slightly different topic from traditional image processing. It is related to more to storage and transmission of the images. So in this, we will see how the image data can be compressed into to reduce the size in memory. Then we will see morphological image processing techniques. They are related to, so here we come to the mid-level image processing. So morphological image processing, then image segmentation, they are related topics. So we will discuss about these in the next presentation. So just I am discussing the topics which we will cover. Then representation and description, then image registration and object recognition. So object recognition touches the area of machine learning, or you can say pattern recognition. So that will be the last module, and we will discuss some topics of object recognition. The evaluation scheme will consist of 3 tests of 15% each weightage, and all of will be like open book. We will see if some component we will conduct in some other way also. Then there are quizzes also. 3 quizzes will be there, 5%, 10%, and 10%. And the comprehensive exam of 30% will be there. So consultation hour, I will announce separately on the Photon. And so you can send me emails if you have any doubts, and I will discuss them in any particular hour. Sometimes in lecture also we can discuss if it is a good topic to discuss. And if it is some other question, I will reply on email also. So you can send me a particular query on email also. The notices will be put on Quanta or Photon. And makeup policy, only in genuine cases it will be considered. So please do not request for any unnecessary makeup requests. And prior permission will be necessary for these makeup. So this is about the handout. So particular dates of the evaluation components I will work out, and this handout will be posted on the Photon. So let us see the introduction of this course, digital image processing. So I hope this screen is visible to you. So the contents of this course, this presentation includes the what is the digital image. Then we will see the digital image processing various stages, and then some applications. So these applications will make you interested about this course. where there is a wide scope of this course in different applications. So we will discuss them also. So what is a digital image? So first step or stage of any digital image processing technique is to acquire the image or image acquisition. So in image acquisition, we have some object. So this object can be a 3D object or a 2D object, and there is a light falling on it. So I am saying the light in a general term. The light can be any electromagnetic wave. So this source of illumination can be any electromagnetic wave or electromagnetic source. And the reflected energy of this electromagnetic source is captured through this imaging system. So this imaging system can be a camera or some other type of detectors. And this reflected energy is plotted, or you can say detected by a sensor. So the sensor, there can be a sensor which is suitable to capture that electromagnetic energy coming from the imaging system or from the object. So that sensor will record the data by converting the electromagnetic energy into voltage and currents. So that will be stored in the form of voltage and current into the memory. So the memory will be in the form of digital memory. So you can say that here this continuous or analog data is converted into digital format. Okay. So here this image you can see on this, you can say image plane or you can say sensor also. So in both form, the electromagnetic energy which is captured is continuous, and this is converted into digital format inside, and this data is recorded in the memory, or sometimes it is transmitted directly using the communication channel. So in both possibilities we have to compress the data also to use the communication channel in optimized manner. We have to reduce the size of data, so that is possible using image compression. So that also we will discuss. So here you see that image is digitized in both space and as well as in intensity. So if you remember, there were photographic film cameras were there in earlier days. So those capture the analog form of the images, but these days we have digital cameras. So those cameras record the image in digital form. So this is similar representation of image acquisition or image formation. The object using an imaging system is energy is incident on an image plane, and it is captured and recorded. So it is digitized in the space first. You can say in the space, there space is consist of grid, or you can say the different discrete sensors. So these discrete sensors will record the energy falling on them in the form of voltage and currents, and that energy is finally discretized again in intensity. So that discretization is in case of amplitude. Okay. So in space as well as in amplitude, both domains, we discretize this image and finally it is recorded. So there is sampling involved here, sampling in the space as well as in intensity. So here you see a continuous gray level from black to white. So this gray spectrum, you can see it is a continuous spectrum from pure black to pure white. So there are different shades of this black color, or you can say uh, black chromation. So this when we digitize in the intensities, or you can say amplitude, then depending on how much resolution we want in the image or what quality of image we want, we discretize accordingly, or depending on our hardware system also. So if we talk about the 3-bit system, so if we want to store the image in the form of 3 bits, each intensity level represented by 3 bits, then we can store almost 8 gray levels. So here you can see that this continuous spectrum of black to white is discretized in 8 gray levels. So 1, 2, 3, 4, 5, 6, 7, 8 from black to white. So these 8 gray levels can be represented by 3 bits. Okay, so using combination of 3 binary bits, we can represent 8 gray levels. If we want more resolution, then we can use 8-bit. So 8-bit is a more popularly used format. So 8 bits in binary format, if you take the 2 to the power 8, it will mean there will be 256 levels. So the black to white region you can discretize into 256 levels or 256 intensities using 8 bits. Okay, so more resolution is possible in intensity if we use more number of bits. Okay, so that will also increase the size of data. So if you want more uh, quality image, then you need more memory storage. So this is just to display the 3-bit system. Then comes the image representation, how we represent the data which we have recorded in the memory. So here you see the example of an image, which is a gray image. So this image contains only the shades of black to white. So it is a 2D array of intensities. And these intensities are in the form of numbers. Okay. So these are stored in the form of numbers, real numbers, 146, 161. So these are all integer numbers. And these integers represent intensity. So this is actually an example of 8-bit image. So in 8-bit image, you may have from 0 to 255 gray levels. So the number you will see in this grid of, or you can say array, 2D array of images is from 0 to 255. 0 will represent the black pixel, purely black pixel, and 255 will represent the purely white pixel. So if you see in MATLAB, we will see in MATLAB also. So in MATLAB, if you zoom the intensity of an image, you will see the numbers. Or you can see in workspace also, the image is represented by a 2D array where in X and Y directions there are numbers are stored, and these numbers are actually 8-bit numbers if the image is 8-bit. So these intensities are recorded using the sensors. So sensor can be a CCD sensor or CMOS sensors in case of digital images. So we will discuss about these also. So we are discussing the gray images especially. So gray images also we can call them monochrome images. So this is another example of a monochrome image. So you can see a part of the image here zoomed out. So this intensities are the numbers ranging from 0 to 255. So 230, 229. So these are all intensities which are representing a gray level. The another aspect of recording the image is quantization. So this quantization refers to the discretization in the intensity level. So sampling refers to the discretization in space, and quantization refers to the discretization in case of intensity. So when we hear the six different quantization levels are represented, where each pixel is represented by, if you see the right bottom image, it is 1 bit per pixel image. So each pixel is represented by 1 bit only, and you know that 1 bit can attain either 0 or 1 intensity. So only two intensity levels can be represented by 1 bit. So this image will have only two intensity levels, either 0 or 1, or you can say either pure black and pure white. So two extremes will be represented by 1 bit. So this image will not have much information, much useful information, because only two gray levels are there. If we see there is four gray levels can be represented by 2 bits. If we represent each pixel by 2 bits, then we can express four gray levels from white to black. So here you see that this image is better than the previous image. If we represent 3 bits per pixel in the form of 3 bits per pixel, we can represent 8 gray levels. So in this way, the quality of the image improves because we are able to represent more gray levels if we are using more bits per pixel. So here the top left image, if you see, it is having 8 bits per pixel, and we can represent 256 gray levels. So this will have very good representation of the image because of good quantization. This next slide represents the sampling information. So how the sampling affects the image. So if you are representing the image on the same size of display, and it is sampled by a factor of 8. So on the top left there is an original image, and if it is sampled by a factor of 2, so suppose we have this original image if is of size 256 cross 256 pixels, and it is suppose captured by a sensor which is having only 128 cross 128 sensors. So then we will have only factor by 2 information. So we if we display it on the same display of same size 256 cross 256, we have to repeat the intensities. So every 2 pixels will have same intensity in that case. So you can see the discretization of this image will be poor than this original image because it is factored by 2. If we factor it by 4, then each 4 pixels will have same intensity. So this uh, uh, bottom left image is 1/4 of the size of this original image, and we are seeing it on the same display of same size. So that's why it is visible as blurred image. It is factored by 4, so it will have 4 pixels with same intensity. Similarly, if we sample it by a factor of 8, then this 8 pixels will have same intensity. So this will be more blurred image. So in this way, it is important to know how the sampling affects the image. Okay, so sampling refers to the discretization in space. So when we capture the image, the sensor size is important because it is the sensor size will uh, decide how the image is being discretized in space. So spatial sampling is related to the size of the sensor. Again, image representation. So we have seen the monochrome images, which are grayscale images. So in the center image is a grayscale image. There can be color images also. So color image, you can see is here represented by RGB, and there are binary images. So these are the three different nomenclature we will use. So mostly we will work on grayscale images, and sometimes we will take the color images also, which we convert to grayscale for easy processing. If to uh, ease the processing of the image, we convert the color to gray image, but we lose the information when we uh, convert from color to gray. And we will also use the binary images in the case of morphological processing. So for creating the mask for segmentation, we have to use the binary images also. So binary images contains only two intensity levels, black and white. So binary images are actually logical. We use them in a logical format. So logical processing operations can be applied on them. So binary images also we will use. So these three you have to keep in mind that we will mostly work on grayscale images, and we refer to them as gray images, not the black and white images. And there are binary images and color images. Now, digital image, if we are observing the color image, so here the upper row is having color image and there is grayscale image in the bottom row. So color images are represented in in most cases are represented by three intensities: red, green, and blue RGB format. So each pixel will have three intensities in red, green, and blue, and the combination of these three colors will produce the final color of the pixel. So this RGB format is important. Then so it is unlike the grayscale images where one pixel represents only one intensity, one gray level. But here the in color images, the each pixel will have three intensity levels of red, green, and blue. So in MATLAB, when we will work out on color images, we will see there are three intensity levels, RGB planes are there for each pixel. So this RGB format is also called true color format. So color images can be represented in true color format. There are other formats also we will discuss in next slides. So this true color format consists of red, green, and blue planes. So if we consider this sub image or section of this image, so this is a 7 cross 7 section of the image. So each pixel is represented by red, green, and blue intensity level. So if you see the first pixel of this image, or is this sub image, so first is intensity of red is 49, green 64, and blue 66. So first pixel will have the color which is produced by the combination of 49, 64, and 66. So this RGB combination will produce a unique color on the pixel. Similarly, next pixel, second pixel is 55, 76, and 80. And like this, each pixel consists of three uh, uh, parts, red, green, and blue. So when we will see it in MATLAB, there will be three planes of intensities, three 2D arrays will be there. So this first plane will consist of red intensities. Second plane will be represent the green intensities, and third plane will represent blue intensities. So the you can see that this color image in true color format will, if you write the size of this image, so it will be uh, m cross n cross 3. So the first dimension represents the number of rows. If I say there are m rows, there will be n columns will be there, and there will be third dimension which will represent the three planes of red, green, and blue. So this RGB planes are three planes. That is the third dimension. Okay. Then there are So again, here it is represented for the monitors. So if you closely monitor the displays, the present displays of any digital display, like the TFT display or LCD displays, if you see them closely, there are red, green, and blue dots are there. So these dots produce the final intensity to our eye. So our visual system of our eyes generally perceives this combination of three intensities as a single color. So it averages out and we see a final combination of intensity using these red, green, and blue pixels. So this RGB format is not a suitable format for storing the data, image data. RGB is used mainly in the printers. In the printers, we see that there are red, green, and blue inks are there, and their combination produces a final color on the printed paper. So this is mostly used in printing, and also sometimes in displays it is used. So each pixel, so there are three pixels which produce the color based on the voltage level. So voltage level will decide which color will be produced on a pixel. So red pixel will attain red color only, but different shades of red color from highest red to lowest red. Similarly, in green shade also, green pixel will also attain only the green color, and blue pixel will attain only blue color. And the combination of these three will produce the final color to our eyes. The next format for storing the color images is index format. So this index format is more suitable for storing the data because here we store only the, so it consists of a 2D plane. So this type of format is useful when our image is having only a limited number of colors in the image. We don't need if you see the 8-bit image, if we talk about the 8-bit image and we store it in RGB format, then we need 24 bits per pixel, 8 plus 8 plus 8 for each red, green, and blue. So 24 bits per pixel we have to store. And those 24 bits will produce, you can say, 2 to the power 24 combinations. So that many colors are possible to create on a pixel. But we don't need that many colors on the actual images. So sometimes we store the image in a more useful format, which is called index format. So this index format consists of a plane of intensities, and those limited number of intensities which we want to display, those are related to a lookup table. So there is a stored lookup table which contains the combination of three intensities, red, green, and blue. So a limited number of colors we can store in a lookup table. Instead of all the 2 to the power 24 combinations, we store only a limited number of useful colors for our image. And each combination is assigned a number, index number. So that index we store in the image plane. So we, instead of storing the 24 bits for each pixel, we need now a lesser number of bits. So each intensity level here, if here this 5 intensities related to this combination of red, green, and blue. So here it is represented in normalized form. So this normalized form is represented by this number. So this this will produce this particular color, this combination RGB. Okay. So this format stores only this lookup table on and in a two-dimensional plane of intensities. The next thing we will discuss in the this course is image file formats. So this is the part of image compression. So these formats are very familiar to you: GIF format, PNG, portable network graphics. JPEG is the mostly used format of images. TIFF is used for storing the grayscale images. PGM, FITS. So these all are different file formats which are standardized by the different bodies of these expert groups of image processing. So this JPEG refers to the Joint Photographic Experts Group. So JPEG is a technique of storing the image or compressing the image, where we compress the image using different steps of compression are there. So JPEG also we will discuss in the image compression module. So JPG consists of different stages of storing the image. Uh, so JPG also has discrete cosine transform it uses to convert the data into frequency domain. So this is a long process where the image is stored in a very small size instead of the true color format. So true color format will represent the actual intensities, and JPEG format will store the image in a very small size so that we can easily store and transmit the image. Similarly, these PNG, other GIF, all are compression format for the images. So they don't store the image in the true intensity form. They convert the intensities into the suitable form to store the data. Morphological processing will be the next module after compression. So in morphological processing, we will deal with only binary images, which will have uh, either pure black or pure white intensities, and each pixel will be represented by 1 bit only. So it can attain either 0 or 1 intensity. So 1 will represent the pure white and 0 will represent the pure black. So since there are only two possibilities are there, so they are referred to as binary images. And we will work on them in morphological processing. So morphological processing deals with the shapes. So these shapes, we will apply different set operations. So if you remember the set operations, which are union and intersection, these type of set operations are there, and equivalent to that there are binary operations like and, or, nor, and XOR. Like these operations are there. So those operations we will apply on the images to convert into suitable form. So here we see an example of fingerprint recognition. So we have a raw image where there are so much noisy pixels are there. So they do not represent any information of the fingerprint. So we have to improve this image. So we want to segment only the fingerprint information from this image. And there are many breaks are there, many we can say many discontinuities are there. So those are all we have to correct. So we will do it in morphological processing. So here some operations are applied, and finally we get this image after processing. So these all operations are performed in morphological processing. Morphological processing we will also use for segmentation, where we want to segment the foreground and background. So any image, if we want, suppose if we talk about face recognition, so if we want to segment the face area for in the image, then we have to apply the segmentation. So we have to create a mask, and that mask will consist of pixels with intensity 1 in the face area, and the background will have 0 intensities. So when we multiply the mask with the original image, we can easily segment out the region of interest or the foreground. So overall, this any image processing system, or if you do the projects, they will consist of these steps. So there will be some problem domain. So problem domain may be any image which may be fingerprint, it may be face recognition, then there will be facial images. If you are working on the, suppose, microscopic images in medical processing, then also biological images. So depending on the image, the problem domain you have to choose. Accordingly, you have to choose the image acquisition system. Now, if you talk about the image acquisition system, it can be a microscope, or it can be a camera, normal camera, or there are different telescopes are there in satellites. So those are also image acquisition systems. In medical imaging, if you see, there are MRI scanners are there, or PET scans are there. Those are also image acquisition systems. So it can be any image acquisition system. So this system itself can have this image enhancement block. So this image enhancement block will enhance the image. So this enhancement will be applied either for the machine perception or by the perception by humans. So suppose if we talk about the medical images like X-ray or MRI scan, so those MRI scan images, the raw images may not be perfect for interpretation by a doctor. So there also we have to apply the image enhancement. Similarly, the satellite images may be corrupted by noise, so those images are also need to be enhanced. Then we have to apply the restoration. So the image, suppose, is sent on a communication channel, then it may be corrupted with noise. Also, while storing the image, also there may be possibility that we may not get the correct image for use in by the machine or by humans. So in that case also we have to apply the image restoration. So image restoration is a process where we try to recreate this model of noise by which the image is corrupted, and using the mathematical models of noise we try to inverse the operation. So that inversing the operation means we are removing the noise or restoring the image, original image, which was stored in a memory or transmitted on a communication channel. So original image we have to restore. So that is the processes we will study in image restoration. Then morphological processing is the next step where we will. So up to here, up to image restoration, this is called low level image processing. Then we come to the mid-level image processing, which consists of morphological processing, segmentation, and this representation and description. So morphological processing will consist of working on the binary images, or separating the foreground and background using the morphological techniques. Then segmentation will consist of segmenting the region of interest. So any region of interest in the image, we will segment out using segmentation techniques. Then these two techniques, which are, this object recognition is the last block. Representation and description is the technique to, suppose in segmentation, we have segmented out the face area in face recognition system. Then face will have certain features. So that face area we have to represent in the form of some features of the image. So those features we will feed to the recognition system or machine learning system. So converting the features of any object into the attributes or numbers to be fed into the recognition system is called representation and description. So this representation and description will create some features or numbers which are suitable for machine learning system. or pattern recognition system. And finally, the object recognition consists of machine learning techniques like neural networks or k-means classifier. So all classifiers comes into object recognition. So if you have any questions, you can ask. So I see here one question which is related to RGB format. So let us go to the RGB format. So any color image, if you see, the color image consists of, so generally if we directly see, we see only the pixels, okay? So each pixel, if you store and see in the, if we will see in MATLAB also. So in MATLAB, if you will see, then each intensity or each intensities image intensity is represented by three numbers. So these three numbers will represent red, green, and blue intensities. Okay. So first number is if you see the first pixel. So first pixel top left number, if you see in all three planes, 49, 64, and 66. So red will have 49 intensity, green and blue. So these three intensities will be there and representing each intensity for red, green, and blue. Okay. So let us, I will show you an example. So I have this image which is spine.tif. So I will display this image. So you can see this is an image of a spinal cord. So this is a medical image captured by MRI scanner. So this is a gray image. So this gray image, if I zoom it, so this is stored in this. Okay, so this is a binary image. So we have to choose some color image. So any JPG image we can take for. So in MATLAB, you can see in command window, you can check if you have used previously the. Okay, so here we see an image, which is a color image. Okay. So it is not actually color image, but it is a JPG format. So you can see in command window, it is stored like 205 cross 269 cross 3. And it is in unsigned integer 8 format. So it is actually 8-bit per pixel format. Okay. So it will have three planes of each of size 205 cross 269. And this third dimension means R, G, and B planes. So red, green, and blue planes will be there. So here we see in the workspace, if we click on this, double click on this image. So here we see the 255 as first intensity, 248, 250. So these are all different intensity levels are there. Each for this, so this is showing the first plane. So colon, comma, 1. So 1 means it is a red plane. So red intensities are represented by these numbers, real numbers, integer numbers, which are 8-bit numbers. So 8-bit means it will be from 0 to 255 only. Okay. So So I think for today the time is over. So I will stop here. So you may have some questions. So we will, I will share these slides and we will continue this presentation in the next lecture also, since the applications are remaining. So we will see the remaining slides in the next lecture. The recorded video, I will share the link on the Quanta. So you can see the recorded lecture. So I will stop here. We will continue from here. Okay, thank you.